My name is Hassan and welcome to my thesis defense. Today I will talk about the work I've done as part of my PhD. DRAM has been prevalently used as the main memory due to its low latency and low cost per bit. Over the last 2 decades, DRAM chip density improved greatly due to continuous manufacturing technology node scaling. Today we have access to 32 gigabit DRAM chips that power various computing systems. Obviously, it is desirable to increase the DRAM chip density even further for increasing the main memory capacity. However, transitioning to smaller technology nodes exacerbates the scaling challenges of DRAM. What are the scaling challenges of DRAM? As DRAM cells become smaller and the distances between cells reduce, ensuring data integrity becomes an increasingly critical problem. Often ensuring reliable DRAM operation limits the minimum latency for accessing DRAM. So typically DRAM vendors make design decisions that affect the data integrity versus latency trade-off in DRAM. Consequently, the DRAM scaling challenges affect the system performance, energy efficiency, reliability, and security. In this thesis, to combat the system-level implications of the DRAM scaling challenges, our goal is to first build an infrastructure for characterization, analysis, and understanding of real DRAM chips. Second, enable new mechanisms for improving DRAM performance, energy efficiency, reliability, and security. Here is our thesis statement in line with our goal. Understanding DRAM characteristics and operation through rigorous experimentation using real DRAM chips paved the way for developing new mechanisms that significantly improve DRAM performance, energy consumption, reliability, and security. We make 4 core contributions that support this thesis statement. In our first contribution, we built SoftMC, a flexible and easy-to-use FPGA-based DRAM characterization infrastructure. Our second contribution, U-TRR, develops a new methodology to uncover the inner workings of in-DRAM RowHammer protection mechanisms for studying their security properties. Our third contribution is self-managing DRAM, a simple interface and DRAM architecture for enabling autonomous and efficient in-DRAM maintenance operations, which can help solve the RowHammer problem along with making other DRAM maintenance operations more efficient. And finally, in our fourth contribution, we propose CROW, a low-cost and versatile substrate for improving DRAM performance, energy efficiency, and reliability. Before going deeper into each of the 4 contributions, I would like to give a brief background on DRAM organization and operation. Here I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside a DRAM chip, there are multiple banks which contain many DRAM cells organized as a 2-dimensional array. A DRAM cell stores a single bit of information as electrical charge. The cells are vertically connected to sense amplifiers, which can read the data from the cells and update it if needed, and cells are organized horizontally as DRAM rows. Now let's look at DRAM commands that the memory controller issues to access the DRAM. To perform an access, the memory controller first activates or opens a row by issuing an activate command. The activate command loads rows data into the sense amplifiers where the data can be accessed. After the row is accessed by a set of read and write commands, the memory controller issues a precharge command to close the open row so that a new row can be opened. This is basically how DRAM is accessed. Each DRAM cell encodes data in a fundamental leaky capacitor. Here is a simplified diagram of a DRAM cell where the capacitor stores the data and the access transistor gates access to the data. There are a number of leakage paths by which charge can enter or exit the capacitor. Because of this, the data stored in DRAM can be corrupted if too much charge leaks. This is a simplified diagram of cell capacitor voltage over time. Due to charge leakage, the cell voltage slowly decreases. When cell voltage drops below the Vmin threshold, we may not be able to correctly read the data that was originally stored in the cell. In order to prevent failures from charge leakage known as retention failures, periodic refresh operations are issued to restore the capacitor voltage. Next, I will talk about the first core contribution of this thesis, the SoftMC infrastructure. There are many factors that affect DRAM reliability and latency. Some of these factors are violation of DRAM timing parameters, inter-cell interference, manufacturing process variation, temperature, DRAM supply voltage, and others. Because many of these factors cannot be properly modeled in simulation or analytically, we need to characterize, analyze, and understand the behavior of real DRAM chips to design, evaluate, and validate mechanisms that could improve DRAM reliability and performance. I would like to explain the 2 goals that we believe a DRAM characterization infrastructure should achieve. First, a DRAM characterization infrastructure should be flexible so that it can support testing any DRAM operation. The infrastructure should enable issuing the DRAM commands in any order with adjustable and precise timing between these commands. Second, the infrastructure should be easy to use. It should have simple and intuitive programming interface that minimizes programming effort and time. It also should be accessible to a wide range of users. Even users that lack experience of hardware design should be able to perform DRAM tests. We designed our infrastructure to achieve these goals. Our infrastructure, SoftMC, is the first publicly available FPGA-based DRAM characterization infrastructure. SoftMC is easily programmable using its C++ API. This photo shows an example SoftMC setup where the FPGA runs SoftMC and has a DRAM module attached to it. The SoftMC user controls the experiments with programs that run on the host machine connected to the FPGA via the PCIe interface. To perform temperature-controlled experiments, this setup uses two heater pads sticked on both sides of the DRAM module and adjusts the temperature of the DRAM chips using a temperature controller. Also, to control DRAM supply voltage, this setup uses an external power supply unit that powers the DRAM module. Let me quickly show the research that SoftMC has enabled since its release. This slide shows publications which use different versions of SoftMC from our Safari research group. I would like to specifically mention Trespass because this is related to the second contribution of this thesis. In Trespass, we show for the first time how to bypass RowHammer protection mechanisms implemented in current DRAM chips. SoftMC has also contributed to research from other research groups. In summary, SoftMC is the first publicly available DRAM characterization infrastructure. It is flexible and easy to use. The source code of SoftMC is available on GitHub. SoftMC enables many new studies, ideas, and methodologies in the design of future memory systems. We will now discuss our second contribution, U-TRR, which is an example research that SoftMC enabled. To protect their DRAM chips against RowHammer, DRAM vendors currently implement proprietary RowHammer mitigation mechanisms typically called target row refresh or TRR. The key idea of TRR is to refresh nearby rows upon detecting an aggressor row. We demonstrate how TRR operates at a high level. The TRR mechanism detects an aggressor row as a result of repeatedly activating and precharging the same row. To protect the neighbor victim rows from experiencing RowHammer bit flips, TRR refreshes the victim rows by performing TRR-induced refresh operations. TRR refreshes victim rows by piggybacking TRR-induced refreshes to the refresh commands that the memory controller periodically issues. Although this is how TRR operates at a high level, different vendors implement TRR differently, and the exact operation of these TRR mechanisms is unknown. Therefore, TRR is obscure, undocumented, and proprietary. Because of this, today we cannot easily study the security properties of TRR and make sure it is fully secure. Our goal is to study in-DRAM TRR mechanisms to understand how they operate, assess their security, and secure DRAM completely against RowHammer. We propose U-TRR, a new methodology to uncover the inner workings of TRR. The key idea of U-TRR is to use data retention failures in DRAM as a side channel to detect when a certain row is refreshed by TRR. I will explain the high-level operation of U-TRR with an example experiment. Initially, U-TRR identifies a set of DRAM rows that have similar retention times. Let's assume the retention times of rows 0, 1, and 2 are T. In the diagram, we represent the weakest cell in each row with circles. At time 0, U-TRR initializes the rows with to charge state. If the 3 rows remain closed for T, we expect the weakest cells to lose a significant portion of their charge and observe retention failures at time T. However, if any of the rows get refreshed, for example, when we issue a ref command at time T over 2, the refresh row should contain correct data at time T. To test when the TRR mechanism selects which rows to refresh, we perform multiple experiments where we change the number of times an aggressor row is hammered. For example, activating row 1 5 times may not make the TRR mechanism refresh any of the neighbors. However, activating row 100 times may trigger neighbor row refreshes. And we can observe this from the retention success on both row 0 and row 2 at time T. Because different TRR mechanisms operate differently, we need to perform many such experiments to understand how they detect an aggressor row and when they refresh the victim rows. Using TRR, we analyzed 15 DDR4 DRAM modules from each of the 3 major DRAM vendors. Through this analysis, we understand TRR operation and craft new custom RowHammer access patterns that cause RowHammer bit flips in TRR-protected DRAM modules. Our results show that first, all 45 tested modules are vulnerable to our new RowHammer access patterns. Second, our access patterns cause at least 1 bit flip in almost all DRAM rows in many modules. This makes system-level RowHammer attacks easier to mount, as the attacker would have the ability to cause bit flips in almost any DRAM row. Third, we observe that our access patterns cause up to 7 RowHammer bit flips in an 8-byte data word, making ECC ineffective and systems equipped with ECC also susceptible to RowHammer attacks. We conclude that TRR does not provide security against RowHammer and can be easily circumvented using the new understanding provided by U-TRR. In summary, we propose U-TRR, a new methodology that leverages the data retention failures in DRAM to uncover the inner workings of TRR and study its security. We use U-TRR to analyze 45 DDR4 DRAM modules, and we find that the new RowHammer access patterns cause a large number of RowHammer bit flips. We believe and hope that U-TRR will facilitate future research by enabling rigorous and open analysis of RowHammer mitigation mechanisms, leading to the development of both new RowHammer attacks and more secure RowHammer protection mechanisms. We released the source code of our implementation of U-TRR on GitHub. Now let's discuss our third contribution, self-managing DRAM, which is a new DRAM interface and architecture that allows implementing efficient DRAM maintenance mechanisms, including mechanisms for RowHammer protection. Today, the memory controller is in charge of managing DRAM maintenance operations, such as DRAM Refresh, RowHammer protection, and memory scrubbing. Because of this, changes to maintenance operations must often be reflected to the design of memory controller, DRAM interface, and other system components. Therefore, such changes are only possible with a new DRAM standard, which takes a long time to develop. For example, there was a 5-year gap between DDR3 and DDR4 standards and 8-year gap between DDR4 and DDR5 standards. This makes implementing new maintenance operations or modifying the existing ones difficult to realize. Our real goal is to, first, ease the process of enabling new maintenance operations, and second, enable more efficient in-DRAM maintenance operations. We propose self-managing DRAM, or SMD for short. The key idea of SMD is to prevent the memory controller from accessing DRAM regions that are under maintenance by rejecting row activation commands. To provide a DRAM chip with the ability to reject an activate command, SMD slightly extends the existing interface between the memory controller and the DRAM chips. SMD adds a single negative acknowledgement ACT pin to a DRAM chip, which the chip uses to signal the memory controller that it rejects the latest activate command. Leveraging SMD's ability to reject an activate command, a maintenance operation can be implemented completely within a DRAM chip. Performing a maintenance operation on an entire bank would cause a large portion of the DRAM to become inaccessible during the maintenance operation. Therefore, SMD divides a bank into multiple lock regions and performs maintenance operations at a smaller granularity. The size of a lock region can be configured at design time. SMD uses a small lock region table, LRT, to mark locked regions that undergo a maintenance operation. LRT stores only 1 bit per region, and a typical SMD configuration with 8 regions per bank requires only 8-bit LRT per bank. When the memory controller sends an activate command, SMD checks if the row to be activated belongs to a locked region. If so, SMD rejects activate by sending the memory controller an ACT signal. Now let me explain the high-level operation of SMD. Let's assume that the memory controller attempts to activate a row in lock region 0. When the DRAM receives the activate command, SMD checks the LRT table. Because LRT indicates that lock region 0 is locked, SMD sends the memory controller an ACT signal. Because the activate is rejected, the memory controller retries the same activate command after ACT retry interval, at which point lock region 0 is available for access. While waiting to retry the rejected activate command, the memory controller is allowed to attempt activating a row in a different lock region in the same bank or in any lock region in a different bank. Using the self-managing DRAM architecture, we develop various maintenance mechanisms. For DRAM refresh, we develop a fixed rate refresh, which uniformly refreshes all DRAM rows with a fixed refresh period. Also, we develop variable rate refresh, which uses retention profiling information to skip refreshing rows that can retain their data correctly for extended periods. For RowHammer protection, we develop probabilistic RowHammer protection, which performs neighbor row refresh with a small probability on every row activation. Second, we develop deterministic RowHammer protection, which identifies frequently activated rows and refreshes only their neighbors when needed. Last, we develop a mechanism for memory scrubbing, which is SMD-MS. It periodically scans the entire DRAM for errors and corrects them. Thanks to SMD, all these mechanisms can be implemented completely within DRAM, and they can operate together. Now let's look at the performance and energy benefits of SMD when using variable rate refresh and deterministic RowHammer protection and memory scrubbing. To evaluate the performance and energy benefits of SMD, we use emulator and DRAM power. We simulate 44 single-core workloads. The thesis also includes results for multi-core workloads. We simulate a system with 4 dual-rank DRAM channels and 32 millisecond refresh period. This plot shows the average speedup achieved on single-core workloads with SMD-based maintenance mechanisms. The speedup results are normalized to conventional DDR4 DRAM. As a comparison point, we also show the speedup of hypothetical DRAM that does not require refresh or any other maintenance mechanism, denoted as ideal DRAM. SMD-based mechanisms provide 9.2% speedup, which is close to the speedup that the hypothetical ideal DRAM achieves. The second plot shows the DRAM energy consumption normalized to conventional DDR4 baseline. We observe that SMD saves about 6.3% DRAM energy, and this is close to the energy savings of ideal DRAM. We also have multi-core evaluation results in the thesis, and the results are similar. So besides making new maintenance mechanisms easy to implement, SMD also improves system performance and energy efficiency. Let's quickly look at how SMD-based maintenance mechanisms perform for different refresh periods. This plot shows the speedup of SMD when using 64, 32, 16, and 8 milliseconds refresh period. The speedup is normalized to the performance of conventional DDR4 with the respective refresh period. We observe that SMD-based refresh mechanisms provide greater performance benefits at lower refresh periods. SMD achieves 19.5% speedup for 16 millisecond refresh and 51.5% speedup for 8 millisecond refresh period. In both cases, SMD performs close to the ideal DRAM, which shows that SMD eliminates most of the overhead of the refresh operations. We conclude that SMD-based refresh mechanisms will become even more beneficial to employ in future DRAM chips that are expected to require more frequent refresh. Please refer to the thesis for more detailed evaluation results. In summary, the 3 major DRAM maintenance operations are refresh, RowHammer protection, and memory scrubbing. We observe that implementing new and efficient maintenance mechanisms often requires difficult-to-realize changes in various system components, including the DRAM interface and the memory controller. In this work, our goal is to first ease the process of enabling new DRAM maintenance operations in DRAM and enable more efficient in-DRAM maintenance operations. To this end, we propose self-managing DRAM, which enables implementing new in-DRAM maintenance mechanisms with no further changes in the DRAM interface and the memory controller. According to our evaluations, SMD-based maintenance mechanisms achieve significant performance and energy benefits across many system configurations and workloads. We released the source code of SoftMC on GitHub. We will now discuss the fourth contribution of the thesis, CROW, which is a subset that provides different ways of optimizing DRAM latency and reliability. We observe that modifying the density-optimized DRAM cell array structure often incurs high area overhead. Therefore, it is difficult to efficiently solve the scaling challenges of DRAM by directly modifying the underlying DRAM cell array. Our goal is to lower the DRAM access latency, reduce the refresh overhead, and improve DRAM reliability with no changes to the DRAM cell architecture, and with only minimal changes to the DRAM chip. Reducing refresh overhead and improving DRAM reliability overlap with goals of efficient maintenance operations, but the cross subset is more general as it also enables DRAM latency reduction. To this end, we propose CopyRow DRAM, or CROW, a flexible subset that enables new mechanisms for improving DRAM performance, energy efficiency, reliability, and security. The key idea of CROW is to add flexible and dynamically manageable pair rows called copy rows that enable in-DRAM row copy and simultaneously activating 2 duplicated rows for fast row activation. We use CROW to develop 3 mechanisms. We propose CROW cache, which uses copy rows to enable low latency access to most frequently activated rows in each subarray. CROW cache reduces row activation latency by 38%. Second, we propose CROW ref, which reduces refresh rate by remapping a retention-weak regular row to a strong copy row. CROW ref eliminates more than half of the refresh requests. Third, we propose a mechanism for mitigating RowHammer, based on dynamically remapping a potentially victim row to a copy row. We'll leave the detailed evaluation of this mechanism for future work. We propose CROW, an in-DRAM subset for addressing the 3 key challenges of DRAM scaling. CROW introduces copy rows in addition to regular rows in conventional DRAM. A copy row provides 3 key benefits. Using the CROW subset, we develop CROW cache to enable in-DRAM caching, CROW ref to reduce DRAM refresh overhead, and a mechanism for mitigating RowHammer errors. We believe CROW will enable many other use cases going forward. Now, I would like to conclude my talk. We discussed 4 core contributions towards understanding and solving the scaling challenges of DRAM. These 4 contributions provide evidence for our thesis statement. Understanding DRAM characteristics and operation through rigorous experimentation using real DRAM chip paved the way for developing new mechanisms that significantly improve DRAM performance, energy consumption, reliability, and security. We have released the source code of the tools that we developed as part of our 4 thesis contributions. We hope and believe that our contributions will enable future research in understanding the characteristics of current and future memory systems and encourage more innovation in the area. Some promising research directions are more detailed characterization of DRAM behavior, extending SoftMC to support other DRAM and even NVM standards, improving RowHammer attacks and defenses, developing more efficient in-DRAM maintenance mechanisms, and developing new mechanisms that take advantage of in-DRAM data movement mechanisms. During my PhD, I had the opportunity to contribute to research in various DRAM-related topics. Here's a timeline that shows the publications that I was part of, grouped by topic and a year of publication. During my PhD, I also contributed to works on topics other than DRAM. Before I conclude my talk, I would like to thank all people and organizations that made this work possible. Specifically, I'm grateful to my advisor, Onur Mutlu, my PhD thesis committee, Safari group members, internship mentors, industry sponsors, family, and friends. Thank you for listening to my talk. Now I'm happy to answer any question.